Hello, Bacho, and welcome. Today, we're tackling a very important topic from our chapter on moving charges and magnetism.
We're going to learn about the force between two parallel currents. Now, this idea is very, very simple, trust me, and I'll make sure it's super easy to remember for your exams. It's not just some random formula, It's about really understanding how electricity and magnetism are connected, and getting this right is crucial for scoring well.
So, here's what we'll cover. First, a surprising force to get you thinking. Then we'll see how wires actually attract. After that, the official physics formula, and we'll build it step by step. We'll also look at common exam traps. You don't want to fall for those. And finally, we'll wrap up with a summary and see how this all connects to the definition of the ampere.
Okay, let's dive right into our first section, a surprising force.
Have you ever seen two lightning bolts in the sky? It's quite a sight, right? But did you know they can sometimes actually pull towards each other? Why would that happen? I mean, lightning is just a huge electric current. The answer, my friends, is hidden in the physics we're about to learn today.
All right, let's move on and see exactly how these wires attract. What's the core idea? The fundamental reason is actually quite simple.
Look, it's a simple two-step process. Think about it. A current in one wire, what does it do? It creates a magnetic field around it, right? Now, this magnetic field goes out and exerts a force on the second wire. That's it. It's an interaction. One wire makes the field, the other wire feels the force from that field. Simple as that. Okay, so we've got the basic idea down. Now it's time to get into the official stuff, the exact NCRT formula you need for your exams. So the force per unit length between two parallel conductors is this. We write it as small f, which equals mu naught times IA times IB, all divided by 2 pi d. Now, what does force per unit length mean? It simply means the force acting on every single meter of the wire. Let's quickly break down what each symbol means. F, as we said, is the force per unit length, measured in newtons per meter. Mu naught, you know this one, it's the permeability of free space, just a constant value. IA and IB are simply the currents in our two wires, wire A and wire B, and D is the distance between them. See, it's really just a relationship between the currents and how far apart they are.
So, a very important question is, where does this formula even come from? We're not just going to memorize it, right? Let's build it up step by step so it makes perfect sense.
Okay, just follow me here. It's a three-step story. First, wire A, with its current IA, creates a magnetic field around it. We'll call it BA. Simple enough. Second, wire B is just sitting there at a distance D inside this magnetic field. It's now in the zone of influence of wire A. And third, because wire B has its own current, IB, and it's in that magnetic field BA, it experiences a force. It's that simple. One creates a field, the other feels a force in that field. And this picture shows it all perfectly. Look, you have two conductors, A and B. The current in A creates a magnetic field, BA. If you use your right-hand thumb rule, you'll see the field goes into the page where B is. Now, B is carrying a current in that field. Apply Fleming's left-hand rule, and what do you see? The force, FBA, is pointing towards wire A, and that means they attract. Let's try a really simple worked example to see this in action. Imagine the current in wire A is 2 amps, and in wire B, it's 3 amps. And let's say they're 1 meter apart. We just plug these numbers into our formula. So the force per unit length, F, is, well, you see the calculation here. It works out to 12 times 10 to the power of minus 7 newtons per meter. See? Just plug in the values. Okay, now for a very, very important section. I call these the silent killers in exams. You have to pay close attention here because this is where a lot of students lose marks unnecessarily. This is the big one. In electrostatics, what did you learn? Like charges repel, and opposite charges attract. Simple. But here, in magnetism with currents, it's the exact opposite. Please remember this. Like currents going in the same direction, they actually attract. And opposite currents, going in opposite directions, they repel. It's the complete reverse of what you're used to with charges. Don't get this mixed up. All right, let's start to bring this all together. So, why is this topic so important? Is it just another formula to remember? No, absolutely not. This idea is the very foundation of how we define the unit of current itself, the ampere. So here it is, the official definition. The ampere is the steady current which, if you have it in two long parallel wires that are 1 meter apart in a vacuum, would produce a force of 2 times 10 to the power of minus 7 newtons for every meter of length.
This definition comes directly from the formula we just studied. It's not magic. We use the physics of this force to define what 1 ampere actually is.
And this number, 2 × 10⁻⁻7 newtons per meter, this is so important. Please star mark this value in your notes. It's a very common question in MCQs. They'll ask for the force per unit length used in the definition of the ampere, and this is your answer. Don't forget it.
Okay, so let's quickly summarize the key takeaways from today. First, parallel currents attract, anti-parallel currents repel. Very important. Second, the force happens because one wire's current creates a magnetic field that affects the other wire. Third, the formula for the force per unit length is F equals mu naught IA IB over 2 pi d. And finally, this whole interaction is the basis for the official SI definition of the ampere. That's everything you need to know. And just to leave you with something to think about, a single moving electron is basically a tiny, tiny current, isn't it? So, does that mean that every moving particle in the entire universe is constantly exerting these magnetic forces on every other one? It's a pretty amazing thought, right? Think about that. We'll explore more in our next session. Until then, keep studying hard.